All right, this is 15.1, day number 2, inverse trig. Day 2, we're going to talk about composition of inverse functions, values, and variables, a little bit with identities as well. So this is a good problem for you to be aware of and work on your own time. I'll make a separate video for this. I would like for you and a neighbor, or by yourself if you don't like your neighbors, I would like you to work on these 5 problems. I'm going to give you 5 minutes. One of them is a Mark Wahlberg snipe, and I guess half of you are going to get sniped. Go. All right, we're back. So here we go. We're going to take the cosine of some angle. I'm going to call this angle theta. And arctangent, as we know, as well as arcsine, they're restricted to quadrants 1 and 4. Okay, so I know that since the tangent is positive here, it'll be in quadrant 1. So I'm going to sketch a triangle in quadrant 1 with a tangent of 4/5. If I use Pythagorean theorem, I should get the square root of 41. This right here is theta. So the cosine of theta would be adjacent over hypotenuse, which would be 5 over root 41. If you got there, that is a good answer. If you wanted to go further, you could rationalize, which would give you that. Either of those is acceptable test answers. Okay, for problem number 2, I'm going to be taking sine of theta 1 plus theta 2. Theta 1 is in quadrant 1. Theta 2 is also in quadrant 1. I'm going to use those to draw 2 triangles in that quadrant. So let's start with theta 1. Here's theta 1. I have a cosine of 2/3. 2/3. That's a 3. That should make this side the square root of 5. Okay, that's theta 1. Theta 2. I'm going to draw a separate triangle. I have a tangent of 4/3. That should ring a bell here. That makes a 3, 4, 5 right triangle. That's theta 2. So now I'm going to use this formula right here. Sine of theta 1 plus theta 2 is sine of the first angle, cosine of the second, plus sine of the second, cosine of the first. Okay, that's a formula you need to be aware of and comfortable with. So sine of the first, let's do this. Sine of the first will be root 5 over 3. Cosine of the second will be 3/5 plus sine of the second, which is 4/5. Nice thing about these problems is you will always have a common denominator already built in. Cosine of the first will be 2/3. So as I write this out and combine like terms, it looks like I get 3 root 5 plus 8 over 15. I would leave it like that. I would not try to go further. That's good. All right, let's jump into number 3 here. 3, 4, and 5. We have not hit the Mark Wahlberg special yet. I'm going to call this thing right here theta. I'm going to draw it in the first quadrant. Cosine is 1/3. Adjacent, hypotenuse. That makes this square root of 8. Okay, that's JV. That could be 2 root 2, I believe. Yep, 2 root 2. If you wanted to go varsity there with it. So the cosine of 2 theta would be cosine squared theta minus sine squared theta. So let's write these out here. Let's do this piece here. Cosine squared theta. Well, we're going to take the cosine of that, which is 1/3. We're going to square it. And then we're going to subtract sine squared. And sine is going to be a little bit more complicated. Maybe I'll leave it as root 8 to keep it simple. Yeah, I think I will. Let's take root 8 over 3 and square that. That's going to give us 1/9 minus 8/9, which would be negative 7/9. Did you do good on that? Were you good on? Were you good kids? Yeah, okay, good. All right, now, this fourth one here could be just a recognition thing, or it could be draw a triangle. It's totally up to you. But I see 1/2 as a unit circle worthy value. So what would that be? Pi over what? Pi over 3, good. Okay, if you ever see arc cosine on the very outside, or arc sine or arc tan, that tells you you're going to have an angle. Up here, we didn't have any angles. Why? Because I was asking for the cosine, the sine, and the cosine. Those give you ratios. Okay, so arc cosine and inverse sine will give you an angle. So here's the snipe, if you didn't catch it or not. Did anybody get an answer for this? For number 5? It doesn't exist. Here's why. I draw the triangle, well, arc sine is negative in the 4th quadrant. What's wrong with that picture? The hypotenuse cannot be shorter than one of the legs. Done. Doesn't exist. Okay, I want to connect this to one more thing, and it might like go in your brain like a good explosion. If there's a good explosion in your brain. Let's look at sine for a second. 2 pi, right? Pi over 2, 3 pi over 2. This is your friend. Okay, where is -4 on the y-axis? Way down here, right? Not to scale. Does the graph ever cross -4? No. So if you're taking the arc sine, arc cosine of a value, what can that value not exceed? 1 or -1? Yeah? So whatever this thing is in here, for arc sine and arc cosine, oh, don't think of that as division. For either one of these, this number right here cannot be greater than 1 or less than -1. Not possible, because the hypotenuse always has to be larger than the leg. Good? Okay, now at this point, I want you just to focus up here. You could write things down if you'd like, but I just want this to be focused time on this. This should be on, isn't this on there? Keep going, a couple slides. It's got a circle on it. I just adapted it, changed it a little bit, because I didn't need the circle. So I didn't do that for you because I cared, but I didn't have enough time. Okay. What's the difference between these two examples? Cosine of x, cosine of 2x. So what would happen to the graph of cosine of 2x? Does it get stretched or shrunk? No. Shrunk horizontally, right? So it's on the inside. So that means that if I were to, say, take a cosine graph, somewhat like this, that means in that same amount of time, there, oh, no, there, 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 there. That means that this graph would be shrunk. So if I were to take and try to find a solution, how many solutions would there be on the black graph? 2. How many solutions on the green one? 4. So this number right here, this number will double the number of solutions between 0 and 2 pi. It'll double that. What if it were cosine 3x? How many solutions then? 6. What if it were cosine 12x? 24 solutions. So it's squashing it so that there's that many more solutions. It oscillates quicker. So I'm going to introduce you to something that's Well, very interesting here, and it might, the first time through, not make a whole lot of sense, but we'll go with it. Let's take this here. I could solve for x, which is going to be an angle or a side. An angle, right? By doing this, inverse cosine of root 3 over 2. Between 0 and 2 pi, we've said how many solutions would there be? 2. Kind of. Ready for this? Now how many solutions will there be? Only one. Okay. So there will only be one solution here. There can only be one solution here because we're using inverse or arc. Now, if I gave you these specific instructions and said 0 to 2 pi, then there'd be 2. Okay? If I said find all solutions between 0 and 2 pi, then there'd be 2 solutions. Okay, we'll get to that in a moment. What if I said, actually, let's find these first. Let's find the restriction based on this first, and then we'll find the restriction on this second, the number of solutions based on that restriction second. So where is this true? Would it be in the first or second quadrant? First, right? What would it be? Pi over 6. So x would equal pi over 6. Okay, let's just mark that here. That would be right here, right? Pi over 6. If now we opened it up to 0 to 2 pi, there'd be another solution right there, right? It'd be 11 pi over 6. Okay, so I know then that I'd have 2 solutions between 0 and 2 pi. Okay, now this might get kind of interesting here, so let's just jump into it. But let's say I wanted all possible solutions. How many solutions would there be? An infinite. So I don't want to write them all out. So what I would do is I'd go pi over 6 plus 2 pi as many times as I want. That only takes care of half of the infinite number of solutions, right? The other half would be this. As many times as I want. Let me pause there and take questions. Why would I need this? Why wouldn't I just add 2 pi to pi over 6 and get all of them? Right? Because if I add 2 pi to that, it just gets me back there. It doesn't cover my bases at the fourth quadrant solution. Okay, now I want you to work with a neighbor and see if you can come up with, this would be the answer to the second restriction. Or actually, this was the, no, whatever. Here's all possible solutions. I'd like you to do the same thing on the second problem. Think about it now. There's going to be double the number of formulas. Twice the number of formulas. Take a minute and I'll come back and I'll clean it up. Let me give you one hint. Does anybody think they have an idea of how they want to do this? No? What do you say? Ha! Okay, so if I did the same thing I did on the first problem over here, that would mean 2x equals the inverse cosine of root 3 over 2. So 2x would equal pi over 6 or 11 pi over 6. So that means 2x equals what? Excuse me, hold on. What would that mean x equals? Pi over 12 and 11 pi over 12. But hold on. That's still only 2 solutions in 0 to 2 pi. Before, what I did was I added 2 pi k to it. But now what am I going to add to it? Pi k. Because I divide everything by 2. I divide everything by 2. Thanks, Mr. Best. Totally in the way. would you please come up with, let's go with the first, let's go the first 8 solutions. How about that? Go with the first 8 solutions. That'll be from 0 to 4 pi, right? Come up with the first 8 solutions from 0 to 8 pi. I'll help you with 0 to 2. I'll help you with 0 to 2 pi. You find 0 to 4 pi. I think I said 8 pi, but I meant 8 solutions. What would our solutions be in 0 to 2 pi? I know 2 of them. Pi over 12, and what else? 11 pi over 12. So we add pi to both of those. What pi is the same as how many pi over 12? 12 pi over 12. So I'm going to add 12 to pi over 12. 12 to 1 pi over 12, which would give me 13 pi over 12. And I'd add 12 to 11, which would give me 23 pi over 12. What is 23 over 12 really close to, but just a little bit short of? 2. It's just short of 2 pi. Okay? Find the next 4 solutions after that. What would I do to those? No. How am I getting from there to my next set of 4 solutions? Nope. I'm just adding what to it? 2 pi. I'm going to the next time around. So 2 pi, I'm going to add 2 pi, which is the same as adding 24 pi over 12. What is 1 plus 24? What is 13 plus 24? 35. What is that? 47? And 47 over 12 is just short of 4. Just short of 4 pi. Correct. So what did I do here? This is what I did. I want to keep it, I know this doesn't look simple, but I want to keep it simple. What is k for this solution? K equals 1 in our first formula. No, I'm sorry, k is 0 in our first formula. Okay, in our first formula, what was k here? 1. In our second formula, k equals 0. In our second formula, k equals 1. In our first formula, k equaled 2. In our first formula, k equaled 3. In our second formula, k equaled 2. In our second formula, k equaled 3. Nice part is we only ask you for solutions between 0 and 2 pi. And if we ask you for all solutions, what you would do is you would not write any of that out. You would just write this. That would be the answer for all possible solutions. This would be your answer. Well, between 0 and 2 pi, we'd have to add in 13 pi over k, pi over 6, and what was that? 20, no, it's short. $23 pi over, for 0 to 2 pi, I'm sorry, these would be your answers. Let's pause and take questions. All right, I'm gonna scratch this for just a moment. And I'm not doing this because I did anything wrong. I'm doing it because I think there might be a better way to do this. Draw a triangle. There's always, whenever dancing's involved, it's better. We determined that between 0 and 2 pi, this would be true in 2 locations. Pi over 6, 11 pi over 6. Agreed? If I wanted all possible solutions, then we would say x equals pi over 6 plus 2 pi as many times as I want, and x would equal 11 pi over 6 plus 2 pi as many times as I want. Good? Solutions here for 0 to 2 pi. Solutions here for all possible solutions. Done. Okay, so I'm going to generalize it over here. Use a different color. So we agreed that 2x would equal the inverse cosine of root 3 over 2, which tells us that 2x would equal pi over 6 plus 2 pi k as many times as we want, or 2x equals 11 pi over 6 plus 2 pi k as many times as we want. Now, x would then equal pi over what? 12 plus pi k, and x would equal 11 pi over 12 plus pi as many times as we want. These are your general solutions if you wanted all solutions. At that point, you'd be done if it said give all possible solutions. If it said between 0 and 2 pi, if it said between 0 and 2 pi, this formula right here would render you 2 solutions. Pi over 12, and then 13 pi over 12. Oops, that shouldn't be plus. The second one would render you 11 pi over 12 and 23 pi over 12. Is that clearer? Maybe? Less steps. All right, I think I got too deep into the algebra. Okay, I think that's good for today.